Hello friends. So today this is the part 3 and the last part for the year 2020, and in this we are going to solve total 6 questions. Out of these 6, 4 are from the mains and 2 are from advance. So this is our total 6 questions. And this is the last part. We have already covered in first and second part only the main questions, and this we consider is inclusive of 2 advanced as well as 4 main questions. So in the first question we are given that a compound microscope consists of an objective lens of focal length 1 centimeter and an eyepiece of focal length 5 centimeter with a separation of 10 centimeter. The distance between an object and the objective lens at which the strain on the eye is minimum is n by 40 centimeter. The value of n is. So in this entire question, the important, you can say, description or explanation or the point that is to be considered is that the strain on the eye is minimum. Okay. And this is going to tell us that the strain on the eye is minimum is going to give us the position of the final image. Okay. So it means if you want our strain to be minimum, the final image formed by the eyepiece should be at infinity. So we have to remember this part very distinctly. So from here we can say that the final image should be at infinity. And we can just write the things which are given to us. We are given the focal length of the objective lens, that is our f0 is given. So we can say our f0 is our 1 centimeter, and eyepiece focal length is also given, that is a f of e is our 5 centimeter, and the separation between the two is given as 10 centimeter. Okay. That is our L, or in some case it is also written as capital D, that is given as 10 centimeters. So in this case the final image should be at infinity, but there will be also an intermediate image formed by the objective, and that will be at the focal point of the eyepiece. You can say that the intermediate image formed by the objective must be at the focal point of eyepiece. Focal point of eyepiece. So which basically means that it will be 5 centimeter in front of the eyepiece, because the focal length of the eyepiece is given as 5 centimeter. So you can say 5 centimeter in front of eyepiece. So we can say that the image formed by the objective lens with respect to the we can write that image formed by the objective lens, its distance if given as V0, then we can say V0 will be equal to total length minus focal length of the eyepiece, and which comes as 10 minus 5, giving us 5 centimeters. Now we can use the lens formula for the objective lens. Lens formula for objective lens. So you can say this will be 1 upon f0 is equal to 1 upon v0 minus 1 upon u0, and focal length is given as 1. So this comes as 1 upon 1 is equal to 1 upon 5 minus 1 upon u0, and from here we get our 1 upon u0 is equal to 1 upon 5 minus 1, and this gives us that our u0 is equal to this will be over minus 5 upon 4. Okay. And so it means, because if you consider the only magnitude, it is given to be n by 40, so we can say this is equal to n by 40, and we are only interested in magnitude, so we can say our n upon 40 is equal to 50 upon 40. We can divide and multiply by 10, so this gives us the value of n is equal to 50. So value of n is our 50. Next question, and it states that a prism of angle A 1 degree has a refractive index mu 1.5. A good estimate for the minimum angle of deviation in degrees is close to n by 10. The value of n is. So here it is talking about minimum deviation, and minimum deviation is based on directly the formula. We know that minimum deviation is equal to a times mu minus 1. A is given our 1 degree, and it is 1.5 minus 1, which comes as 0.5, and it can be written as 5 upon 10, which is nothing as per the given question is n upon 10. From here we can say value of n is equal to 5. So we have value of n is equal to 5. Next question, and it states that a double convex lens has a power p and same radii of a curvature r of both surfaces. The radii of curvature of the surface of the planoconvex lens made of the same material with power 1.5 p is. So we are given that we have a double convex lens. One second. Okay. And we are given a double convex lens, and it says that it has the same radius of curvature of both the surfaces. So we have a double convex lens which will be something like this, and it says that both radius of curvature is same. So this will be also r, and this side will be also r, and its power is given as p, and we have its refractive index is not given to us anyways, if I'm not wrong. Okay, so we can use the formula for the power, for focal length, and we know that our 1 upon f will be equal to mu of lens, suppose it is refracted as mu, and we have 1 upon r1 minus 1 upon r2. Here our r1 will be equal to plus of r, and our r2 will be equal to minus of r. So this gives us that our 1 upon f will be equal to mu minus 1, and this comes as 2 upon r, and power we know is our 1 upon f. There we can say the power will be equal to mu minus 1, and this comes as 2 upon r. And in the second case, we are given that we have a planoconvex lens and it is made up of the same material, but the only difference is the power, that is 1.5 p. So we can draw an approximate figure for that also. So this is a planoconvex lens. Same material means the refractive index will be same, and let us assume that the radius of curvature is our r prime. So other radius of curvature, the second one will be equal to infinity. Therefore we can say its focal length for planoconvex lens we can write that 1 upon f prime will be equal to mu minus 1, and this comes as 1 upon r prime. And here let us suppose the power is our p prime, which will equal to mu minus 1, and this comes of 1 upon r prime. And the relationship between this p and p prime is given to us. Okay, so we can say that our p prime is equal to 1.5 times p, or we can say this will be over 3 by 2 multiplied by p, and p is our mu minus 1, and 2 upon r, and we can also substitute this our p prime. So from here we get our mu minus 1 is not equal to, multiply by 1 upon r prime is equal to 3 by 2 multiplied by mu minus 1, and this becomes 2 upon r, and our mu minus 1 cancels out, and 2 and 2 also goes away. So we can say that our r prime is equal to r by 3. So the option number 3 is the correct one. Option 3 is correct. Next question. It was asked in the year 2020 advance, and this question is more or less based on concept. And it states that a parallel beam of light strikes a piece of transparent glass having cross section as shown in the figure below. The correct shape of the emergent wavefront will be. Figures or schematic are not drawn to the scale. So we are given this glass. On the one side it is having a perfect straight and other side is a curved, and that curves is, you can say, in a different shape like a crest and trough, and light is incident on the plane surface and it is going to come out of this curved surface, and we need to find out the wavefront of the emergent. And this we can say, we can make an approximation based on two different things. First is according to the shape. Let me draw the shape. So for this particular shape of the wavefront, for the lens, especially for this one, and that will be similar for this one also. Okay. These two surfaces will be acting as a converging surface. So this will be a converging, as well as this will be also converging, whereas this middle one is going to act as a diverging. And this is basically because of the shape of this particular, let us call this as 1, this as 2, and this shape as 3. Okay. So 1 and 3 will be almost same. So for 1 we can just draw it that the output will be the converging one, and therefore we get the waveform will be coming something like this. That will be just opposite of the, so we are going to get this will be 1, this will be from the 2, and this will be our third. And we can also make an approximation based on the optical path that is being traveled by each, you can say, light ray. So for part 1 and part 3, the optical path will be on the higher side, or they will be same also, whereas for this 2, the optical path will be lesser one. Okay. And the optical path, because of the thickness, it will be traveling, you can say, as compared to the distance. So you can say that the optical path, let us call this as 1, 2, and 3. So you can say the optical path length, optical path length of ray 1 and 3 is greater than the 2. Okay. So based on this, we can also say that the actual output will be like this. And for converging and diverging, we can also, I think this is sufficient. No, need to, so based on this we can say the option number A is the correct one. Next question. It was also asked in the year 2020 advance, and it states that a large square container with thin transparent vertical walls filled with water, a refractive index 4 by 3, is kept on a horizontal table. A student holds a thin straight wire vertically inside the water 12 cm from one of its corners, as shown in schematically in the figure. Looking at the wire from this corner, another student sees two images of the wire located symmetrically on each side of line of the sight as shown. The separation in centimeter between the images is. So we are given basic figure. So we have this square and it is filled with water, and this is our wire which is placed vertically, and the line of sight is exactly through the corner, and the observer is seeing two images which are symmetrically about the axis, which is shown something like this. So these are two images which are symmetrically about the axis, and we can just say we need to find out the distance if these are the two images, and this is not according to the scale, so this is just approximation of the given question in terms of the figure. And we can just draw this figure for the solution of the question, and we are given that there is an object. Okay, we are only interested in this path. Okay, let us call this as A, B, C and D. This A, B and C, D are not of much of importance. Only thing that will be important will be our from AC and DC, and both AC and DC, they are going to behave in the same way, so we are only going to discuss with respect to AC, and that can be replicated for our you can say DC also. And this is our line of sight, and from here we have our eye, and the object is suppose somewhere here. This is our object, okay. And we are given that there are two images formed, so one will be in the top side, other one will be in the bottom side. So let us draw a ray of light, and let us suppose this is the normal. A ray of light is going to strike somewhere here, and it is going to move something like this. Other ray of light from the object, it is going to move from here, and it will try to bend in this direction. And if we extend them both, we can just find the approximate. So this is our approximation of our image I1. Similarly, there will be on the downward side also there will be image. Okay. And let us, this is our O, we call this point as A, this point as B, and we have this is normal N. I think this will be sufficient. We can just go on and explaining it. Okay, and we can just draw, this will be the height of the image from here, and this will be same. Let us call this as height as H. Okay. And we get this as A, B, C, and let us call this as point D, okay. And this point as our E, and this is our F. And so we have our ray of light from object O, ray of light from object O, and we can call that we have an angle of incident and a refraction. Okay, so let me draw this into a clear one. So this is our point B, and ray of light is normal, so this is our angle of incident, and it refracts this way, and this we get our angle of refraction. Okay. And we have our so this is our normal N, and this angle will be our 90 degree, and this is our point O. So therefore you can say that this is given to us as a square. Second, yeah, so this is given a square, so sides of the square are 90 degree, so this will be our entire 90 degree, and we get from here that this angle will be over 45 degree. So we can say that we are going to have this angle will be over 45. Yes. So if this angle is 45, so we have two parallel lines. So one is over this one, and another one is over this one. So we can say our R will be also equal to 45 degree. So we can say that our angle of R, sorry, not angle of R, the refracted angle rather, you can say refracted angle that is given as R will be equal to 45 degree. We can use the Snell's law at point B. So you can say Snell's law at B, we get this as, this is, let us suppose, our we have its refractive index water. Okay, so let us call this as mu1 and this as our mu2. Therefore we can say that our mu1 sine of I is equal to our mu2 sine of R, and mu2 is nothing but our air, so we get this as 1, and mu1 is given to us as water, that is 4/3. So from here we get the value of our sine of I, so we can write it this as sine of I, mu2 is our 1, so this comes 1 upon mu1, mu1 is our 4/3, and we have this as sine of R. Sine of R is our 45 degree. So we get this as 3/4 multiplied by 1/√2, and this comes approximately equal to 0.5303. Therefore we get our I is approximately equal to 32.03 degree. Now we can use this point, we call this as A. So this is our point A. So we can use triangle AOB. You can say in triangle AOB, we can find out that our this entire angle OBA, so this entire angle will be our 90 plus I. So you can say our angle OBA will be equal to 90 plus I, which comes as 90 plus is our 32.03, and this comes as 122.03 degrees. And angle A is our angle A, that is our is already 45, so we can find out our angle O. Therefore we can say that our angle O will be equal to 180 minus, and this comes as 45 plus 122.03, and this comes as approximately equal to 13 degree. Now we can use the sine law and find out, because we are already given the position of the object. This distance is given to us as 12 centimeter, and from here we can find out our what will be our AB. So you can say using sine law, we can say our 12 upon sine of 122 is equal to AB upon sine of 13. So we get this, our AB will be equal to, this comes as 12 upon sine of 122 multiplied by sine of 13, which comes approximately equal to 3.1833 centimeters. Now we can use the triangle, our this is our okay. Here let us suppose we have This point we called it as D. So we can use triangle BAD. So we can say in triangle BAD, and we can easily find out our, let me draw it here. So this is a B, this is a D and A, and we have this as 45, and we already found out AB. So based on this we can find our BD. Okay. So we can say that in triangle BAD, sine of 45 will be equal to, this will be our BD upon AB. So we get our BD. So we get that our BD will be equal to AB. AB is our 3.18. Sine of 45 is square root of 2, 1 upon square root of 2 rather, and this comes equal to 2.25 centimeters. So we found out our BD, and BD is nothing but equal to our EF. So these two are equal. So you can say BD is equal to EF. So we can say our BD is equal to EF. So which we have denoted as H. So H will be equal to 2.25 centimeters. So we found out this was our, this was our height H, and we call this as our E, and this our point as F, and we call this as image I1. So we found out the height of the image I1. So you can say this is height of image I1, and like we did for our side, this was our, one second, sorry, let me rename this. This is our A, because I can use this thing as A, and let us call this as A prime now, much more convenient. So we sorted out for our this side A prime A, and we got the height of our I1. Similarly, we can solve it for our AD, this side also, and we are going to get this height of I2. Obviously that will be symmetric for that, so I2 will be also equal to same. You can say similarly I2 will be equal to 2.25 centimeters. Therefore we can say that the distance I1 and I2 will be equal to 2 into 2.25, which comes as 4.50 centimeters, and approximately, if required, we can just write it as 4 centimeters. So we get this as 4 centimeters. Okay, and beside this I forgot to, you can say, upload one question. Okay, let me get the question first. Then we can discuss the solution for that. Yes. So the question states that we have a point-like object is placed at a distance of 1 meter in front of a convex lens. Of focal length 0.5 meters. A plane mirror is placed at a distance of 2 meter behind the lens. The position and nature of final image formed by the system is. So we need to find out the position and the final image of the system, and here it is a combination of, you can say, both a lens as well as a mirror. Okay. And the mirror is given as a plane mirror and the lens is our convex lens. So first is our convex lens, so we can just draw an approximate figure for that. So let us suppose this is our principal axis. We have a convex lens, let us call this a lens L, and we have somewhere here the mirror as M, and we are given that we have a point object at a distance of 1 meter in front of the lens. So this distance is given as 1 meter, and plane mirror and the distance between lens is given as 2 meters, and we are given that focal length is 0.5 meters of the lens. So its focal length is 0.5 meters. We need to find out the final image of this entire system, that is combination of lens as well as mirror. So first image will be formed by the lens, and that image will act as an object for the mirror, and then the ray of light will be reflected back from the mirror onto the lens, and that will be resulting in the final formation of the image. So total there will be 3 images. One image formed by lens, then there will be image formed by the mirror, and finally once again the image will be formed by the lens, and we need to find out the final image that will be formed. So let us start with our lens. So we can say image formed by the lens formed by the lens. Let us call that as our I1. We can use the lens formula directly. We get 1 upon f, 1 upon v minus 1 upon u. Focal length is our 0.5 and v, let us suppose this is our v1 and u is our minus of 1. So we get this as minus of minus 1. So we get our 1 upon v1 will be equal to, this comes as 1 upon 0.5 and this is minus of 1. Okay, and 0.5 is our 10 divided by 5, that is 2. And we get this 2 minus 1, so we get v1 is equal to 1 meters, which is the position of our I1. That is, it means somewhere here in the midpoint we are going to get our I1, and the distance of this I1 from the lens will be our 1 meter, and similarly from the mirror total distance is 2, so this will be also our 1 meter. And this image will be acting as a object for the mirror M. So you can see this I1 will act as an object for mirror M. And for mirror, we know that the distance between the mirror and the image, which is basically here an object, will be same as its final image. Therefore, we are going to get an image that will be, let us suppose, our I2, and the distance from the mirror will be same, that is our 1 meters. We can say that the image formed by mirror M will be at 1 meter. Let us call that as our I2. Now this I2 will be acting as an object for the lens. You can see this I2 will act object for the lens L, and the total distance will be of this I1 from the lens will be equal to 3 meters. Therefore, we can say that our for lens, our objective distance, that is our U2, will be equal to 2 meters. Sorry, not 2, 3 meters. And we need to find out the final image. So once again, we are going to use the same formula, that is our 1 upon f is equal to 1 upon v minus 1 upon u. So let us call this a v2 and u2, and we need to find out our v2. We get this as 1 upon v2 is equal to, we have this as 1 upon f, and we'll minus of 3, and this comes as 1 upon f will be equal to minus of 1 upon u2 and let us write this plus. If you substitute the value, this comes as 0.5 minus of 3, and once again this will be about 2 minus 1 upon 3, which gives us that our 1 upon v2 will be equal to, this comes as 6 minus 1, that is 5 upon 3, which gives us that our v2 will be equal to 3 upon 5, and this comes as 0.6 meters. And we need to find out the position of the final image of the system. So we can say the final image will be so here in the options we are given that we need to find out for with respect to the mirror basically, and therefore we can say that from the mirror, and mind it, this v2 is from lens, and distance between the lens and the mirror is 2, so we can say from the mirror we get our, this will be 2 plus 0.6, which gives us 2.6 meters, and this will be the real image. Yeah, so this completes all the questions from the year 2020, and in order to complete this we divided this entire question series of 2020 into 3 parts. Part 1 and part 2 was consisting mainly of the mains part, and this part 3 consisted of mains as well as advanced part. So this completes all the questions. Thank you.